Welcome back to module 1. We have discussed time dependent Schrodinger equation, and then with the help of variable separation method we have been able to get the wave function. We have got the idea of stationary state and superposition state. Superposition state is absolutely needed to observe the temporal change in the probability density, which is all about the quantum dynamics, because that is the only way we can observe the motion of quantum particle. Now, we have said that the phase is very important factor, and because phase is an important factor, let us say I give an example here. P orbital we often express as positive and negative lobes like this way. Now, if I consider this P orbital and express the orbital the wave function, total wave function, then I would express like this way. It is going to be, this is 3-dimensional, so instead of x I will consider r here as a vector, and x I will consider r here, and then its characteristic phase factor minus I e t by h cut. So, what it suggests that if I try to observe its wave function, p orbital wave function, and somehow if I can manage to get how does it look like as a function of time, I will see that after a certain time it has changed its phase, again after a certain time it has changed its phase, again after a certain time it's changed its phase, but total density does not change, and that is the meaning of the stationary state. This phase becomes important when we talk about combining two different wave functions. For an example, we know that this wave function, if they are combining like this way, so they do not combine because of this negative and positive phase. They do not combine, and that is why they form kind of a anti-bonding state. They form an anti-bonding state, and bonding state is just the reverse one. So, phase becomes very important. Phase is a physical quantity which describes its the wave function motion, but its density is not may not depend on that phase unless we create the superposition state. We, after having understood these ideas, one can now introduce more rigorous mathematical definition of the wave function, the time dependent wave function. Obviously, it is going to be a superposition wave function, because that is exactly where we are interested in quantum dynamics. It has to be superposition state, and or it has to be a wave packet, and the wave packet, more general mathematical form, is going to be this: its expansion coefficient, its time independent part, and the time dependent phase factor. We are adding them infinite number of states. If the states are discrete like this, we can start from n equals 1 to infinite number of states. We can add them together and form this wave packet. This kind of mathematical expression, what is the origin of such superposition that we have described. Without superposition, we will not be able to see the change in density. So, anything relevant in quantum dynamics which is practically relevant, or which can be used for to observe experimental quantities, that is related to this kind of wave packet. And if the states are continuous, like I cannot distinguish, all the states are available, kind of continuous states, then I can use this integration directly. This is called continuous state, is some kind of continuum, let us say. So, in that case I will be able to integrate from 0 to infinite over this dE states. So, these are the two more mathematically rigorous definition of the superposition states or the wave packet. We will use this kind of expression later for the mathematical derivation, but the origin of such equation comes from those two state superposition states we have discussed in the earlier session. The real test of understanding what is going on is to solve some of the problems, and in next two examples will be given. One is electronic superposition state, how do we create electronic superposition state, and another one will be given vibrational superposition states. So, we will start with electronic superposition state. We will start with this example of H2 plus. H2, when H2 makes bond, it actually coming from A and B we have given to designate the particular hydrogen atom. So, two 1s orbitals, they linearly combine together. This is called LCAO method, linear combination of atomic orbital. This linear combination of atomic orbitals, when they combine positively, they form this sigma bond, and this sigma state, because it's an one electron system, this ground state can be represented by this, where R0 is the distance between these two atoms, H2 atoms, hydrogen atoms. We have fixed it at a particular fixed R0. We have linearly combined two atomic orbitals, 1s from each orbital, and we get the ground state wave function of that H2 plus system. And the ground state wave function has a symmetry notation, and that is given by sigma 2 sigma g plus. Group theory is related, and using group theory one can find out how to give the symmetry nomenclature of a particular electronic state. This is not the scope of this course, so we will not go over that part. We will assume that we understand how to give the name, the symmetry notation for a particular electronic state. So, ground state has this symmetry, and excited state. So, basically what is going on, I have one electron. So, electron can stay here. If electron is staying here, I get ground state. If electron is staying in the here, then I get one excited state, and that excited state is nothing but the antibonding sigma antibonding orbital, which is given by negative combination of these two 1s orbitals again, and this is given by this wave function. So, there are two wave functions I have right now, two electronic states I have, one here, one here. Both states, and H2 plus can stay here, H2 plus can stay here also. If H2 plus is staying only in this state, that is called stationary state. If H2 plus is staying only in the excited state, excited electronic state, that is also stationary state. But somehow, if I manage to create a superposition state linearly combining both states, what will happen? Interesting thing will show up. Now, how do we create such a superposition state? That is a different question. We can use some kind of laser photoexcitation which can simultaneously excite these two states together. That is possible, but that is not the point of discussion here. The point of discussion here is we create the superposition state by linearly combining these two electronic states. So, if we linearly combine these two electronic states, then what will happen? Here I will mention that LCAO is also linear combination of two atomic orbitals, but there is a difference between superposition state and LCAO scheme. LCAO scheme does not include the temporal phase factors of individual atom. So, superposition state, the superposition scheme is different from LCAO scheme. In superposition scheme, we have two states. We will linearly combine these two states with its characteristic phase factor. Phase factor is going to be EGT by H cut, and this one is going to be minus EIUT by H cut. Its corresponding energy is Eg, here is Eg, and Eg, and this is Eu. So we will consider those corresponding phase factor and then linearly combine it. What we will have is following. I have these two states and I can write down, because these two states are stationary states, I can write down its time dependent states as R comma T, then semicolon R naught. When I say semicolon, it means that R naught is constant, internuclear distance has been kept constant, and R is the is representing the electronic coordinate, and R naught is representing nuclear coordinate, which is kept to be fixed. So the time dependent wave functions can be written as this space dependent wave functions Ig R naught multiplied by e to the power minus I Egt by h cut. Similarly, the excited state wave function, time dependent wave function, can be written as with its corresponding phase factor. So we have assumed that the this internuclear distance doesn't change, it is kept to be constant. The equilibrium geometry R naught, we have kept it constant. And so what we will do is that we will create the superposition state right now, and the superposition state we will create by taking the total electronic wave function of the superposition state is given by linearly combining these two states. These two states we have already written, and if we linearly combine them, we get this wave function. We create this wave function. Now all we need to do is that this wave function is not an important thing. We have to find out the density, because in the end we have to check how the density is changing. So I will write down the density expression here, psi r comma t r naught. Total density is going to be following psi star r comma r comma t semicolon r naught multiplied by psi r comma t semicolon r naught, which is nothing but psi g star r comma e to the power I. This is complex conjugate, that's why negative sign is gone from this side, h cut, plus psi u star r naught. This is again complex conjugate, that's why negative sign is gone, multiplied by psi g r naught e to the power minus I Egt by h cut plus psi u r naught e to the power minus I ut by h cut. So we multiply this. It's just tedious multiplication, that's all, but it's very simple. So if we multiply, then we get its individual components, that is psi g ground state plus psi u excited state plus cross term, which is psi g r psi u star r e to the power I u minus eg t by h cut plus is complex conjugate, the other part of this wave function. And we have seen that whenever I have e to the power I theta plus e to the power minus I theta, we basically get 2 cos theta. We get back the real part, and we can simplify this equation as psi g r naught, these are r naught square plus psi u r naught square plus 2 psi g, these are all r naught r naught u r naught e to the power sorry, this is becoming cos part, so this is going to be cos u minus eg t by h cut. So this is the equation we get, which is nothing but this delta energy difference. EU minus EG is going to be the energy difference of these two states. And because this is, as I mentioned before, this is going to be the real part, these are all real part. So this can be considered as real because psi g is nothing but 1 by square root 2 phi 1s a plus phi 1s b, both are real, and psi u equals phi 1s a minus phi 1s b. So both are real atomic orbitals, s orbitals are real, that's why these are becoming a real part. And what we get is from this is that density will depend on time, and it is oscillatory. Oscillation controlled by this cost function, it is oscillatory with a period. The period of the oscillation is going to be cos delta E t by h cut. So this is nothing but omega t equals delta E t by h cut. 2 pi nu is going to be delta E by h cut. Nu is the optical frequency, this is angular frequency. So finally nu I get as delta E by 2 pi h cut, which is nothing but delta E by 2 pi h by 2 pi, which is nothing but delta E by h. So this is the frequency with which density, this density of this system will change, and that's exactly we have shown. The probability density depends on cos delta E t by h cut. This is the term which is going to control the change in density as a function of time. So the moment I create the superposition at t equals 0, we will see that the electron density is localized in a particular atom. It is not delocalized. After a certain time, the electron density will be delocalized over the two atoms, and then after a certain time again electron density will be localized in the other part of the molecule, and this will keep coming back like this way, and it will be keep oscillating. So electron density, if I have hydrogen atom, then electron density in the superposition state, electron density is localized here, delocalized, then again localized here, delocalized, again localized here, delocalized, and this is the way. It's more like an electronic wave, the wave which we see in a sea beach, or the waves coming coming to u and going back is something like that. Electron density is now oscillating as a function of time, and that's exactly the simplest representation of the quantum dynamics, that electron density is moving. And when this electron density in the end moving, it depends on the period, or how fast it's moving. It depends on the energy difference, because we have taken two different states and then linearly combined them. This was Eg and this was Eu. These two electronic states were linearly combined. When we linearly combine them, then the density will depend on this energy difference. For H2 plus, the energy difference is 11.83 eV almost. And because of that, if we plug that in here, then we'll be able to get the period of the time dependent electron density is 248 attosecond. Attosecond is 10 to the 1 into 10 to the power minus 18 second. Extremely fast. This kind of oscillation can happen extremely fast. It's going to be 10 to the power minus 18 second. Within this time scale is oscillating, but this oscillation will be controlled by this energy gap, and that's very important to understand in a superposition state. We will be able to confirm that what kind of oscillation we get is that by the fact that, because in the end my density will be controlled by this simple equation, which is delta Et by h cut. By this expression, we know that cos can take different values. Cos can take 1, cos can take minus 1, cos can take 0 values. And we will consider all these values to find out, to prove that this kind of change in density will be going on in space as a function of time for this superposition state. So what we'll do first, we'll use cos equals plus 1, and that is, and when we get cos equals 1, it means that I am at t equals 0, because cos 0 is actually 1. So at t equals 0 time, this is the time, what will happen, the total density is now can be written as r comma t semicolon r naught whole square equals 1 by square root of phi 1s a plus phi 1s b square. So this is individual wave functions, 1s minus phi 1s b square, plus I have this 2 multiplied by square root of phi 1s a plus phi 1s b multiplied by phi 1s a minus phi 1s b. So in the end, if I simplify it, I'll be able to get half of phi 1s a square plus phi 1s b square plus 2 phi 1s a 1s b plus phi 1s a square plus phi 1s b square minus 2 phi 1s a 1s b plus phi 1s a square minus 1s b square. This part is a square minus b square. So we can simplify further. Phi 1s a square plus phi 1s b square plus phi 1s a square minus phi 1s b square. This gone, I get phi 1s a square. So, it suggests that at t equals 0 time, the density, total density will be localized only on the A part, and that is exactly shown here on the A side. What will happen if we get cos equals 0? If I get this cos equals 0 term, then total wave function, now I will be writing like this way. One is A plus phi 1 is B plus phi 1 is A minus phi 1 is B, which gives me finally, if we simplify it, I am skipping one step, you can check it by rigorously doing this math. This is just tedious. So, what it suggests that at t equals, when t equals pi by 2 h cut by delta E, when this time, that is this time, the density will be delocalized over A and B, and that is exactly what is shown here. Density is delocalized. Now, the another part where cos term is taken to be minus 1, if we take cos to be minus 1, then t is going to be this one, and one can write down psi r t r naught density is nothing but phi 1 is A plus phi 1 is B plus phi 1 is A minus phi 1 is B minus 2 1 is A plus phi 1 is B 1 is A minus phi 1 is B. So, if we simplify it, finally we will see that we get 1 is B square. It means that the density at this time will be localized only on B. This is where it is localized. So, this demonstration shows that, this exercise shows that how the densities are changing as a function of time at different time, and what this periodic change in density is controlled by, inversely controlled by this time period will be inversely proportional to this energy difference between the states which are involved in the superposition, creating the superposition. So, this is a demonstration for electronic superposition state. Electronic superposition can be as fast as attosecond, and how to observe that is a different question, but we can create electronic superposition state by linearly combining two electronic states. Next, we will go over quickly go over vibrational superposition state. When you think about vibrational superposition state, we will again these are the vibrational state generally under harmonic oscillator approximation. We get different vibrational states like this, and one can think about, okay, what about if we consider V equals these two states, if we linearly combine with this characteristic phase factor, what will happen to those states? But before we get into these states, first we will remind few things, and that will help one understand what is all about this diatomic vibration. One of the simplest examples of vibrational superposition state can be realized from a superposition of the ground and the first excited state of the diatomic quantum harmonic oscillator, which we have shown here. We can linearly combine these two states. A quantum harmonic oscillator is a good model for a vibrating diatomic molecule. under this model, diatomic molecule can be represented by a spring, just like the one I have shown here, like a spring, and this is vibrating. When this is vibrating, it's vibrating like two balls are connected by a spring, and spring is compressed, sometimes stretched, then compressed, stretched, and that's a good model for the harmonic oscillator. So harmonic oscillator is a good model for the quantum vibration. And when we have that, we say that two atoms having mass m1 and m2, its equilibrium distance is r0, which is here at the r0 distance. This is your E and this is your R. So this is called r0. When I say r0, it means that one atom is anchored here and another atom is here, and that's why this is called r0. r0 is the equilibrium bond distance, but it can have different bond distance. It can have, I can have vibration like this way. So this can be one distance, that is the r distance. I can have r distance. So different, it can be stretched, it can be compressed, depending on what time of the vibration we are in. Equilibrium bond distance is r0, and r represents the instantaneous bond length during the vibration. Now when we do that, when we think about this one, this two body vibration like this way, which we have presented, the mathematics gets little tedious and difficult to deal with. So often for mathematical convenience, what we do, we define another, to express the same vibration, we define another physical quantity called x. X is the difference between the instantaneous bond distance and the equilibrium bond distance. That's the difference. So we are defining x, and we are defining, so we have defined an x coordinate which is represented by r minus r0, which means that if x is positive, it means I have stretched it, r is greater than r0, and if x is negative, it means that I have compressed it, right? So that's the way we can think about it. In fact, I cannot that's the way we can think about it. And in this picture, this when we have changed the coordinate from r coordinate to x coordinate, we can also, another change we can make a reduced mass. So we can say that 1 by mu equals 1 by m1 plus 1 by m2. If we do that, then this whole two body problem becomes a one body problem given here. And if we perform the math with the help of one body problem, we can easily translate the information to the two body problem. And that is what we do very often in dealing with two body or diatomic species in spectroscopy or quantum mechanics, where in the one body, if we consider the one body system, then the angular frequency which is governing this vibration in the x coordinate is given by square root of k divided by mu. K is the force constant. K is the force constant. So just to remind ourselves that we basically have a diatomic molecule, but to deal with diatomic molecule, I have to deal with this r coordinate and also two body. Instead of dealing with two body, there is a mathematical convenience, or mathematically you can convert this two body system to one body problem. And if we use this one body problem, that I have only one body with reduced mass vibrating with respect to this wall in x coordinate. If we solve it, then we will be able to translate the information to the two body problem. So it is basically simplifying one complicated problem in one dimension, and then solving it and discussing the diatomic vibration. When we do that, we get the wave functions for the ground and the first excited state, vibrational state, where I have shown this wave function. Interesting thing to note that the ground vibrational state in simple harmonic oscillator is actually look like a Gaussian wave function, e to the power minus a x square. It is a Gaussian function. So similar functions we are getting here also. A Gaussian function, and the first excited state wave function looks like this. This wave functions we get from TISC, time independent Schrodinger equation, which can be written as h cut square by 2m. This is the Hamiltonian operator, partial derivative second order, plus half k x squared, that's the potential energy, k is the force constant, psi x equals E psi x. We get set of solutions. We get set of solutions just like this. Any TISC we solve, we get set of solution, and each state is defined by this quantum number v, where energy of that state is given by h cut square root of k by mu v plus half, which is nothing but this is each state is given by this, and they are non-degenerate state in the simple harmonic oscillator, and these are the two wave functions we get. So it is giving an idea to approach a quantum dynamics. First, at t equals 0, before the time evolution, we have to find out, it suggests that we have to find out the stationary states. Once we find out the stationary states, then we have to create the superposition and then let it evolve through this TDAC. That's the basic approach, and that's exactly reflected here also. We are trying to find out with the help of TISC. We have found its possible energy states, and then we are linearly combining these two states to find out its superposition, the behavior of the superposition state. So what we will do here is that the superposition state will be expressed as, this is the ground state, ground vibrational state, this is the first excited vibrational states, explicitly written like this way, where alpha, we have already defined alpha equals square root of k mu by h cut square, system characteristic of the system. Is a constant for a particular vibrating diatomic species. So this probability, if we know the wave function, superposition state wave function, then we will be able to find out the probability density, how it's changing. It is obviously changing like this way. Individual probability we are getting here, plus its phase factor, which I am going to write directly, e to the cos function we are getting, t by h cut. So basically what we have is that this is v equals 0, this is v equals 1. We have linearly combined these two states with its own characteristic phase factors. These are the phase factors we have, and the moment we do that, then the total wave function, the total density, the state, the particle is now in the superposition state created by two vibrational wave functions, and in that state the density is changing as a function of time like this way, which can be expressed as explicitly can be expressed as alpha by pi to the power half e to the power minus alpha x square plus 4 alpha cube by pi to the power half x square e to the power minus alpha x square plus 2 alpha by pi to the power 1 by 4 alpha cube by pi to the power 1 by 4 e to the power minus alpha x square x cos delta E t by h gun. This is between 1 and 0 states. So, we get these expressions, and once we get these expressions, then an interesting point here we can notice here that this total wave function, this density, total density will be evolving as a function of this term. And if we look at this term, this delta E 10 t by 10 by h cut, this is the, so the, this is going to be the omega frequency, and this omega is the frequency of change in this density, this superposition state density. This is created by V equals 1 state and V equals 0 state. These two states. So, what it suggests that omega is the frequency of the vibration. So, these two atoms are vibrating with a frequency omega. Question is, can I observe that vibration? Let us say the system is in the V equals 0 state. If the system is V equals 0 state, we know that even at V equals 0 state, molecules, this diatomic species is vibrating all the time. Question is, can I observe that vibration? No. If it is staying at V equals 0 state, it means that its wave function is going to be represented by psi x e to the power minus I E0 t by h cut, and because its wave function depends, because the system is at V equals 0 state, even if it is vibrating, there is no way experimentally I can observe this vibration, because in the end this is a stationary state. Total density will not be sensitive to the time, because total density depends on its densities, depends on this psi star psi. So, in order to observe that frequency, observe that vibration, what you need to do is that we can create the superposition between V equals 0 and V equals 1 superposition. If we create that, then there is a change in density. That change in density will also follow the same frequency. So, coherence, we are creating superposition state with the help of coherence. This coherence is allowing me to observe vibration in a molecule. If the molecule is staying only at V equals 0 state, that is a stationary state, I will not, although it is vibrating all the time, but I will not be able to observe that vibration. The only way I can observe the vibration with the same frequency is by creating a superposition state between V equals 0 and V equals 1. So, coherence is allowing me to observe the inherent vibration in the molecular system. This may not be true if you do a superposition between V equals 0 and V equals 2 states. Check what is the outcome. Check what kind of frequency you should observe for the density. How does it compare with its own frequency? That can be different. But if we create this V equals 0 and V equals 1 state superposition, then we will be able to observe the same frequency with which the molecule is vibrating. We will now move to similar kind of derivation which we did for the electronic superposition state. We will consider different cos values in the expression, and we will try to find out what is going to happen to the total density. We will start with cos equals 1, which means that I am at t equals 0. If we are t equals 0, then we can write down explicitly density is going to be alpha by pi to the power half e to the power minus alpha x square plus 4 alpha cube by pi to the power half x square e to the power minus alpha x square plus 2 alpha by pi to the power 1 by 4 alpha 4 alpha cube by pi to the power 1 by 4 x e to the power minus alpha x square, which is nothing but alpha by pi to the power 1 by 4 e to the power minus alpha x square plus 4 alpha cube by pi to the power 1 by 4 e to the power minus alpha x square by 2 whole square, which means that I have to add these two functions first and then square it. So if I want to add these two functions, what is these two functions? These two functions was v equals 0 wave function and v equals 1 wave function. That's exactly I have plotted here. V equals 0 wave function, this one is v equals 0, and then this one is v equals 1 wave function. Now phase becoming an important issue. You see, on this side, this part will be added together, it will be magnified, but this part, they are cancelling each other, so they will be diminished, and that's why finally the density will be localized more on this part at the B position than this C position. That's the effect we have right now. So we see that there is a localized density in one part of the molecule. So we'll stop here, and we will continue this module in the next session.